In earlier chapters, we studied single agent search problems, like finding a path in Romania map from Arad to Bucharest, where the environment was fixed and predictable. But what happens when other agents are involved and their goals conflict with ours? This is where adversarial search comes in. In AI, we often study games as models of competitive multi-agent environments. Unlike puzzles or pathfinding problems, here the challenge comes not just from complexity, but from the presence of an opponent actively trying to prevent our success. So, what do we mean by games? Game theory defines game as a multi-agent environment where each agent's action significantly affect the others. This is very important. In economics, games can be cooperative or competitive, but in AI, games are modeled as competitive multi-agent environment. This is a key difference. Why games are interesting in AI? Because games are not just fun, they are hard. We will show you how hard they are. Unlike in pathfinding, inefficiency in games is punished severely. Let's say you play a chess game with computer. If your chess program evaluates half as many positions as your opponents, it will likely lose badly. This challenge forced AI researchers to invent new techniques to balance optimal play with limited time, and this is not easy. Let's see it with a game which we know. It's called tic-tac-toe. See, initially, the person who plays first, everyone wants to win a game, right? The person who plays first puts an X in the middle box. Then in the second stage, the opposition plays a circle in this place. Then again, the first person, the turn goes back to the first person and he puts an X here. Then the fourth state, the person playing second plays a circle here, and then 5 X is put here, and in 6 0 is put here. Then we go to the seventh stage where the person playing X puts an X here, gets 3 in a row and wins. So few things to note here. To win, you have to have your 3 X's or 3 circles in the row, which is the common rule of the game. This is the terminal state of the game. Remember, terminal state of the game. One person who plays X wins means the person who plays circle loses. So it's a zero-sum game. One person wins, the other person loses. Few other things to note. You see there are 2 boxes still remaining. That means we could have also put X and circle there by going for another turn for each of X and circle, but we don't need, because we have already reached the terminal state and the game has a decision now, a utility value or outcome value. So total we can have 9 different total turns, including first and second player. So, but this reached the terminal state and we can stop here. But here another thing to note is that what was the objective of the person playing circle? The objective of the person, of course, that person, he or she wanted to win, but always wanted to thwart the first person. Okay, I will not let him win at least. That's the common sentiment. That's why it's an adversary, it's an opposition, which is trying to stop the first person to win. So when the first person wants to maximize his outcome or win or maximize the profit, the second person tries to minimize or thwart the outcome or gain of the first person. Remember this, we'll come back to this. Now you see, I have already said that the utility or outcome for x is 1 because x has 1. Utility outcome for circle is -1 because that person has lost. And in case of draw, when let's say all the crosses and circles are filled in all the 9 boxes, utility in case of draw will be 0 for both. Remember that. So what I said in summary, these games are deterministic, no dice or randomness. Okay, you can see that what's happening. Turn taking, players move alternately 2 players, simplifies the reasoning. We have already said that 2 players taking turns, 0 sum because 1 player wins, the other player loses. Perfect information because all players see the full state, like in chess or in tic-tac-toe. Of course, you in your mind, you are thinking, oh, where to put, kind of trying to evaluate what is the best place to put. But when you're actually putting your turn, it's transparent to both sides. The other party can see that. So it's perfect information for them to make their own decision. So can we define a game as a search problem? Like we saw earlier, modeled as a tree, a start node, and end node? Yes, we can. Just like pathfinding, we can model a game using standard search components, like S0, which is the initial state, how the board is set up. Okay, start like we had earlier. Players, which player moves next? This is an important thing. This was not there because the multiplayer environment, multi-agent environment, which player moves next. And please understand there can be games which are 3-player, 4-player, possible perfectly, okay? Actions, the set of legal moves in that state, okay? Like I can put X in different positions. Result, what state you reach after you execute an action. Okay, you wanted to put X in a particular place. What after you put that X in that particular place, what is the current state of the board? Terminal test, whether the game has ended or not. Utility values, the payoff. Okay, when you win, you get +1 for tic-tac-toe, something like that. Win, loss, or draw score for player. In chess, in the other way, the utility will be +1 for win, -1 for loss, and half for draw. Okay, both player gets half points. Remember that. So the example in this case of the utility is a terminal state might be a full board with 3 in a row for 1 player. That's the utility. Okay, so now you see we will talk about the branching factor for tic-tac-toe in the next video.